This picture of Mars is about the best we can do from the Earth, where we have to be content to look through an atmosphere that's turbulent and across a gulf in space never less than 56 million kilometers. But in 1971, Mariner 9 flew to within 1,500 kilometers of the Martian surface. This canyon is just 75 kilometers across. The next major step was taken in 1976, when two Viking landers actually put down on the Martian surface to give us views like this. This is a full-scale working model of one of the Viking landers. In this program, we're going to be concerned just with the imaging system. Well, what were the problems that had to be overcome? The leader of the lander imaging team was Tim Much.
When we first considered the design of the Viking spacecraft some 7 years ago, we recognized that we had some unique problems. We had to build a camera system that was light in weight and obviously very durable. We also had to build a camera system that, in the event that we could not store data on board the lander, in that event, the camera could transmit directly to the orbiter or to Earth. In other words, we had to build a camera system that produced data at a rather slow rate. For these several reasons, we decided not to use a Vidicon system, the same system that has been used on Mariner and on many other U.S. spacecraft, but we decided instead to go with something which is called a facsimile camera. And in the design and the manufacture of that camera, we turned to the gentleman on my left here, Fred Huck, Langley Research Center, who was instrumental in setting the basic parameters of this camera.
The facsimile camera is an entirely different instrument than the film camera or the television camera. And incidentally, our Viking lander camera is similar, basically, to the Russian cameras on their lunar landing missions. What you have here is an engineering model, a near working model of the camera, with the inner housing and outer housing removed from the major structure of the camera. You see here an entrance window, a thin slot that hides behind a dust cover so that we do not expose the window to dust on Mars when we're not imaging. This inner housing shows you the entrance window more clearly. And here then is the camera itself. Basically, the camera consists of a scanning mirror, a lens, and photosensor aperture. You will perhaps see here, as I move a scanning mirror, this mirror scans the terrain in elevation relatively slowly up while it requires the light from the surface and rapidly down during retrace. Then the whole assembly steps a small step in azimuth, and the mirror again scans slowly up and returns rapidly, during which time we make another step. And so we sweep out the scene with successive lines that are contiguous to each other. The field of view in azimuth can go from behind the dust cover around 342 degrees, almost a complete panorama, and the pointing angle can go from 40 degrees down to 60 degrees, or a total of 100 degrees. The light that is reflected off the scanning mirror is focused by a lens onto a photosensor array. The photosensor array consists of 12 silicon photodiodes, 11 of which have 3 amplifiers mounted in the same housing. Over the photosensor apertures, we have a small aperture, and the size of the aperture, as well as its distance from the lens, determines the instantaneous field of view or angular resolution of the camera. Of those 12 detectors, 4 of them are covered with an aperture that is 0.04 millimeters in diameter, and it forms an instantaneous field of view of 0.04 degrees. Those are our 4 high-resolution detectors, and they are staggered at a different distance to the lens and focused, consequently, at different points in the scene. and the depth of field of the camera is such that we can image objects from about 1.5 meters to infinity with negligible degradation due to defocus blur. The best resolution that we get around 2 meters away from the camera is 2 millimeters per line pair. Of the other 8 photosensors, 6 are covered with spectral filters. 3 of the filters are in the visual wavelength region and are intended to provide us with color pictures of the scene. 3 others are covered with filters that give us spectral information in the near infrared from 0.4 to 1.1 microns. Those near IR filters, together with the color filters, also allow us to get spectral reflectance curves of the surface and spectral transmittance curves of the atmosphere.
We've just seen how the scene is imaged by the camera and how the signal is produced by the camera, and now remains to be described how the signal travels through the lander and eventually back to Earth. Bill Patterson will describe this particular function.
Each of the landers has 2 cameras on it for stereoscopic coverage. They are both on the front of the lander, and the one is towards me with its scanning in this direction. And on the other side is a mating camera here. The camera electronics are all in the base of the mast, the stub mast by which the camera mounts to the lander, and the signals leave the stub mast encoded as binary signals of 64 gray levels encoded as 6-bit serial data with 512 such groups of pixels per line. The signal goes from the camera into the guidance and simulation computer in the center of the lander, which then shunts the signal to either of 2 transmitters. The first of these is the transmitter which goes to the orbiter, and the orbiter then serves as a relay station to Earth, giving us a high-speed link. This is the antenna which feeds the signal to the orbiter. It looks like a set of small beer cans stuck on the end of some rods. The radiation pattern from this antenna, which operates at 800 megahertz, is upward. It radiates into a fairly large cone so that the orbiter can pick it up as it passes from horizon to horizon, a total cone of about 60 degrees. For direct communications to the Earth, we use a microwave dish, this S-band antenna. It's a parabolic dish with a center radiator that points downward into the dish, and then the beam leaving the dish is a narrow beam of about 10 degrees in total cone angle. The signals are picked up through the Deep Space Network, which has stations all around the world. One in Canberra, one in Madrid, and one in Goldstone are the principal antennas. As the S-band signal reaches Goldstone, the signal is attenuated approximately by a factor of 10 to the 12th. Since the transmitter signal on the lander is on the order of 35 watts, the signal reaching Goldstone, even with an antenna at Goldstone which is approximately 50 times as large as the transmitting antenna, the signal is still only a few picowatts. Inevitably, a few picowatt signals are distorted by noise, principally thermal noise from outer space and thermal noise in the detector in the Goldstone antenna. And so the signals are corrupted, bits are lost, bits are changed, lines are occasionally lost, and the result is that there is a strong need for further signal processing, computer massaging to work out what might have been missing in these parts of the pictures.
The data is received here on Earth at the Deep Space Network, and from there the entire data stream is fed to computers at the Jet Propulsion Lab. Immediately on receipt, the imaging data is extracted from that data stream, fed into a special computer, and it is displayed more or less real time. This is the so-called FOVLIP, or First Order Viking Lander Image Processing display. The picture is displayed as a raw image, and very modest enhancements and filters are applied at that time.
FTIS request number was F1062, tape number DFM138. Total of 28 frames. How did we get 28 frames on one tape?
Getting 25 last night. 3 in a row.
Trying to pay us back?
We're in the second segment now.
Okay. Yeah, which is actually the third segment, probably. The first line, we're on line 700.
Oh, right.
What time is this picture taken, Paul?
Oh, let's look at the D10.
Okay.
Local lander time was Sol 31, 12:01:37.
Okay, and it's 18:32 now, about 6.5 hours ago.
Right. That would make it 3 o'clock Earth time this afternoon.
Okay. Yeah. Yeah, because the shadows, I mean, this rock is obviously coming down, you know, coming out at an angle, and the shadow is pretty straight.
I don't think we've saturated too much of it.
Little stuff up there looks like it might have been kicked out by this lag down there. Well, like sort of right over here. I wonder if some of the tails coming out aren't really...
Yeah, there looks to be like a trail right behind this rock.
Yeah, yeah, just where it gets covered by the RTG cover. Yeah, I really like that ridge out there.
We haven't seen this scene before, have we?
No, not in high res.
Didn't notice that before.
Okay, are we processing this now?
Right, we're doing version 1.
Okay, we ought to be able to get a lot
Stretch.
more of this vesicle stuff out. Okay, we want to get rid of all this stuff now. Do the D-spike
That's version 1, a
Yeah.
D-spike and a contrast
and
alteration.
the stretch.
See if it removes that noise data.
Got it. Okay, now you can see the tops of the rocks are a little bit saturated, but boy, does it ever bring out the detail in that sand.
Right.
Yeah, all the
So-
spikes are gone.
You're happy with that stretch?
Uh,
You want to see the rest of the segments?
yeah, let's run through the rest of the segments and see. Or why don't you just go on to segment... You want to put segment 5 up raw?
Okay.
Okay, all right, yeah, now let's... have we got version 2 yet?
No, just version 1 is completed.
Okay, let's look at version 1, segment 5. Got to bring out, at least be able to bring out a lot of the shadow. Okay, yeah, right in here. We ought to be able to bring out almost all of that and get rid of some of these spikes up in here.
Not really stretchy.
Yeah. Why don't we go ahead and put in the first part of the color?
Okay, the red color is coming in. Yeah, we're going to add green. And the blue.
Okay, let's try the ALS and see what happens. I don't know. You want
Did you
to
see the histogram?
Yeah. You want to put it back up on one?
Yeah.
Let me see what it looks like.
And the green. And the blue.
Yeah, I think we'll buy that.
The more detailed enhancements are accomplished over an area called the Image Processing Lab. And Bill Green will describe a few of the special enhancements that are completed there.
In this facility, we receive the Viking lander camera images on magnetic tape. We read the tape into a computer, and then we have a variety of displays and terminals connected to the computer. We use the terminals to call out particular programs to process the Viking lander imagery. What you see here is a 512 element square Viking lander image segment. This particular image segment contains about 250,000 data numbers that comprise the full image. Each of the data numbers corresponds to an intensity. We use low data numbers for dark and high data numbers for white. This is a listing of a small segment of this particular image. As you can see, even to list a very small segment, and this one is about 30 picture elements square, requires a sheet of computer paper, and a full segment requires quite a pile of computer paper. So there's quite a bit of information that's displayed there on the display. I'm now going to do a couple of examples of very simple image enhancement. In this particular region here, if I display the image completely unenhanced as you see it, the information in that region is not visible because the image has been saturated. The first enhancement of that region that I'll try is a linear contrast enhancement. That's one attempt to bring out the information in this area, I'll try a second enhancement that hopefully will work a little better. Now you can begin to see that I'm picking up detail in this particular part of the image. However, if you look just below it, you can see here that I've lost any information that was visible before. This is an example of the fact that in enhancement, when you're simply redisplaying the information, you can gain things, but at the same time you'll lose things in other regions of the image. A similar process I can do is a high-frequency enhancement, again of the original scene. So let me first put the original scene back up. And now what I'll do is I'll overwrite this scene with a high-pass filtered version of this particular image, and then I'll explain the high-pass filter algorithm. What you're seeing come up is a high-pass filtered version of the original scene. In this particular part of the image, you can now begin to see the subtle detail that's in the dirt area coming out. You can also see on the rocks that we've picked up some of the subtle, higher frequency variation that's present in the rock structure. What you're seeing there was totally invisible, or more or less invisible, in the contrast stretched version. Here again, in this particular enhancement, we've also lost something. What we've lost is the overall shading effect across the image from left to right. This, in fact, does not look like a real scene on Mars, but it is useful for the geologists who are interested in determining the structure and variation within these rocks. It's also of interest to people who are working with the surface properties of Mars. They can get a very good idea of the high-frequency variation on the surface. I'm now going to replace the high-pass filtered version with the raw version of the image, and watch especially the detail on the surface. As you can see again, we've lost some of the high-frequency information, but again, for some scientific applications, we have a much better rendition of the actual surface and the albedo variation across the surface of Mars. What you've seen are a couple very simple examples of the types of enhancement that we can do in this facility. We actually have available on this computer approximately 200 different applications programs. You've seen a couple of examples which are in the area that I call subjective enhancement. In this case, in both examples, we're simply trying to bring out the information that's actually present in the data and present it to the human eyeball. What you're looking at here is actually one of the three components of a Viking lander color image. In this case, you're looking at the red component of a three-color image that's been returned by the Viking lander camera. So all the enhancements I've done for you so far have been on a single component of the three-component color image. We'll now take a look at the full color image as we reconstruct it, again using the pre-flight calibration data and quantitative processing to construct the true color of the surface of Mars. What I'll be showing you now is how we build up a Viking lander color image from the three component spectral channels that are recorded by the camera system. The first thing I've displayed on the color display is the blue diode image. This image has been radiometrically decalibrated, and that is the correct intensity in the blue only. I'll now add the green. What you're now looking at is the mixture of the blue and the green information without the red. I will now add the red as the third component of the color image. What you're now seeing is the surface of Mars as best as we can estimate its color using the pre-flight camera calibration data that has been applied to each of the three components. You might notice up near the upper left portion of the screen, in between or just below the four large rocks, that the surface is in fact a darker texture. That's something that comes out best in a color rendition of these particular images. You don't see it very well in each of the individual components, but when they're merged into a color, you do see albedo information on the surface that you don't see in a black and white rendition. As you can see, the surface of Mars is in fact a rather bright reddish orange, and as you may recall, there was some dispute initially after the first lander landed as to exactly what color the surface was. We're fairly confident of this color because we've obtained the same surface color from both landers, and in fact, after applying pre-flight calibration data, we obtained the same color of the surface whether we record it in the camera 1 or camera 2 position. the surface turns out to be the same color from both camera systems.
The Viking cameras have performed spectacularly. The pictures are very good, and I can find no fault with the performance of the cameras relative to the specifications that we set. Now, the real problem, however, is that the specifications we set were sort of a compromise. 7 years ago, we knew that Viking had a certain limitation. And I guess there were two areas in particular that we settled for a compromise. We achieved what we felt was the best possible, at this time, the best possible linear resolution, spatial resolution. At the same time, we achieved what we felt was the best possible spectral resolution, and indeed the best possible range of spectral sensitivity. So I suppose when we talk about future cameras, we would like to improve both spatial resolution and spectral resolution.
The scanners are exquisitely accurate, and they are a very small fraction of a pixel jitter, and we could simply, by having taken more pixels within a line, have achieved a substantial increase in resolution.
And I think we would end up with being able to improve the resolution, say, by a factor of 3, and that would give us the resolution of the human eye, approximately.
There is, however, a small trick that we could have done on this camera and could do in future cameras. At present, the camera takes the color pictures and indeed all its spectral band pictures when we want a high data rate, line sequentially. That is, it takes first a line of blue, then a line of green, and then a line of red. It would be possible to interleave those 3 lines electrically, take all of those pictures simultaneously, and run the mirror somewhat more slowly. And by running the mirror more slowly and stretching out the sampling time, you could improve the signal-to-noise ratio and make a corresponding reduction in the spectral bandwidth.
The capability that this kind of device that we have, the Viking lander camera, is particularly geared to do well, better than any film camera or Vidicon television camera, is that it can obtain not only images, but that we can also make spectral reflectance measurements of the surface, and the spectral reflectance measurements in turn aid in the mineralogical identification of the material.
And this kind of information could undoubtedly be extended with wider range, with more accurate resolution of the wavelength spectrum, and yield for the sky the same sort of information as we're getting for the ground. I find the sky particularly attractive as an example of what one can do, and as an example more of perhaps of the sort of accidents which happen in scientific research. An instrument that was not expected to have much of a contribution turns out to have contributed substantially to that knowledge, and I'm rather happy about that.
The beauty is that you're principally interested in pictures. You're happy with the pictures you've got.
Yeah.
We say that we can still do better by a factor of 3, which gives you the resolution of the human eye. In addition to that, inside the same envelope, for an additional half a pound or a pound, maybe 2, we then also give you spectral reflectance measurement. Naturally, we will be limited in the capability of how well we can do compared to an instrument that's specifically designed to do that.
I can hardly wait for the next mission.
The next mission to Mars, what sort of mission could that be? Could it be a manned landing? Could we see man in the Martian landscape?